Hello, I'm Dr. Prathano Ghosh, and today I'm going to talk about conjugate beam method, which will compute slope and vertical deflection at any point in a beam or frame. So what is our lesson objective today? Determine the slope at any point in the beam or frame, determine the vertical deflection at any point in a beam, and then definitely we need to know the sign convention for slope and vertical deflection. So there are two theorems are there. Theorem 1, which deals with finding slope at any point in a beam. So what it says, the slope at any point in a real beam is numerically equal to shear at corresponding point. So how do you know which one is conjugate beam and which one is real beam? So real beam is your given beam, whatever the problem statement is given. Then we'll create a conjugate beam, which is kind of a fictitious beam for the real beam. So now we'll compare the slope in your real beam will be the shear at conjugate beam at same particular point. Similarly, theorem 2 will be finding the vertical displacement or deflection at any point in the real beam will be numerically equal to bending moment at corresponding point in the conjugate beam. So the question comes, how do we create the conjugate beam for the real beam? We know conjugate beam is a fictitious beam. So how do you create for that? So there is a particular theorem exists to create conjugate beam. So let's discuss about how do we create conjugate beam. So let's say we have given a real beam, which is the first figure, a simply supported beam of length of L, and we are having just one concentrated load P acting downward exactly in the middle of the beam. So this is your real beam, real support, real loading is given. Now is our aim to convert this real beam to a conjugate beam. So how do you convert? There are certain steps out there. So first step is to draw the bending moment diagram of the real. So once you draw the bending moment diagram, then we need to divide by EI. EI is the flexural rigidity, E is the modulus of elasticity, and I is the moment of inertia of the beam. So first we draw the bending moment diagram. So we know for this just one concentrated load, our bending moment will be PL over 4, which is happening maximum in the middle of the beam, PL over 4. And if we divide the bending moment over EI, it will be PL over 4 EI. And that M over EI diagram will be your new loading in the conjugate beam. So first step, draw bending moment diagram, divide by EI, and draw the new loading diagram in the conjugate beam. So we have our moment value is positive, PL over 4 EI. So that's why our loading diagram in the conjugate beam will be acting upward direction. If bending moment value is negative, then the loading diagram will be downward. So once you draw the M over EI diagram, now we know what kind of loading is acting in the conjugate beam. Next step will be changing the support from real beam to conjugate beam. So how do we change support and how it occurs? So we need to do very, very carefully. So before going into the support change condition, just to make sure that your loading in the bottom picture is PL over 4 EI. So W is PL over 4 PI, just to make sure that part. So once you have that, now is the time to change the support condition. So here is a table which gives guidance to change the support condition. So see very carefully how we can compare the support of real beam versus conjugate beam. So there are 7 conditions exist. So we'll first pick up the condition 3, which is the third row. So let's say if you are having one side fixed, is a cantilever beam. So if you have fixed support, that means our slope is 0 and our deflection is 0. There is no way you can rotate. There is no way you can get a vertical deflection at the wall. So once you have fixed support, remember your shear correlates with your slope, vertical deflection correlates with your moment. So somehow you need to change the support in such a way that if your slope is 0, shear will be 0. If your deflection is 0, your moment will be 0. So how do you make that? If you make a free support, fixed to free, if you change it, then we know at the free end, there is no shear, there is no moment. So fixed will be changed to free. Similarly, free will be changed to fixed, which is condition number 4. So we know at the free end, we are having some rotation, we are having some vertical deflection. And if you make it fixed, we know at the fixed wall, we are having some shear, we are having some moment. We do not know the values, but at least we know that shear and moment is there. Similarly, slope and vertical deflection is there in the free end. So fixed becomes free, free becomes fixed. If we consider external pin and external roller, what is the condition? So we know that pin has some slope because the moment is 0. But the vertical deflection is 0 at the pin or roller support because we have the vertical reaction. If you have reaction, there is no way you can get any vertical deflection. So if we keep the same as it is for the pin and roller support, then we can imagine that we are having shear at the pin, we are having basically shear at the roller. Similarly, moment will be 0 at the roller and moment will be 0 at the external pin. So for pin and roller, we are just keeping the same as it is. We are not going to change any support condition. But for fixed, it will become free. Free becomes fixed. Then you can have some internal pin, internal roller. How that condition will change in the conjugate beam, which is basically your fictitious beam. So in the internal pin and internal roller, the condition is same. We know that theta is there, slope is there, but vertical deflection is 0. So that internal pin becomes hinge, a big change. So when it becomes hinge, you can break at that point. Same thing for internal roller, it becomes hinge. And when it is internal hinge, we know that when it breaks, the reaction develops, but moment is going to be 0. So internal pin and internal roller, which is condition number 5 and 6, becomes hinge. External pin and external roller keep as it is. Fixed becomes free, free becomes fixed. And the last condition, which is condition 7, if you have internal hinge, other way around, within your original or real beam, if you are having hinge internally, so that means we are having some slope, we are having some vertical deflection. So just make it internal roller. So we know internal roller holds moment and internal roller has the reaction, which is the shear. So being said that, we have to remember this change of support condition whenever we are solving any problem for conjugate beam method. This is very, very important table. So now we'll move to step-by-step procedure. So as we talked about that, we can have to make from real beam to conjugate beam. So first we need to create conjugate beam, we need to create our bending moment diagram, then you convert into M over EI diagram, and conjugate beam will have the loading which will be equal to your M over EI. One thing we need to keep in mind, the length is not going to change. Whatever the length of real beam, that will be the same length. Obviously loading is going to change, but length is going to remain same. Now, once you make the conjugate beam, your next concentration will be to find out slope and deflection at particular point. Let's say you need to find out slope and deflection at point C. So that means you need to cut at point C and you need to find out your shear and moment value in the conjugate beam, which will be equal to your real beam's slope and vertical deflection. That's how we are going to solve the problem. And last part is the sign convention. It's very important. How do you know whatever you are finding for slope and vertical deflection? Are they positive or negative? So if slope is coming out positive, that means it is counterclockwise. And if it is negative, then it is clockwise. Whereas vertical deflection, if it is negative, it is downward. If it is positive, that means it is upward. So we need to remember sign convention also. Very, very important part. Now we are going to do one example problem with this cantilever beam, whereas one side is fixed, A is fixed, other side C is free, and we have just one concentrated load, 15 kip is acting exactly in the middle, 6 feet from the fixed wall. So altogether span of the beam is 12 feet. So our aim will be to find out slope and deflection at point C of the conjugate beam by conjugate beam method. Here it is mentioned that EI is constant. So we are going to solve the problem in Microsoft OneNote. So I'm going to close this window and then we're going to open up Microsoft OneNote. So our aim to find out slope and deflection by using conjugate beam method. So here is your beam, cantilever beam, A, B, and C. C is the free end. A to B is 6 feet and B to C is also 6 feet. And we are having only one concentrated load, 15 kips acting at point B. It is mentioned EI is constant. So this is your real beam. So first step, we need to convert from real beam to conjugate beam. And you have been told to find out delta C, vertical deflection is how much, and theta C, how much. These are the two parts we need to do. So as you see, this beam, due to acting of this load 15 kips, it starts to deflect. Everything is zero here at the wall, then it starts to deflect at point C. So this is your vertical deflection. And this is your slope with the tangent. This is your slope. So now our aim to convert from real beam to conjugate beam. So what is the first step? Get the moment about point A, MA. Let's get the moment. Negative MA, 15 times 6. So that gives your moment is at A negative 90 kip feet. There is no moment in between B and C because no loading is there. So only moment develop at point A. So let's draw the bending moment diagram. We see negative bending moment. So we are having A, B, C, and at B it is 0. From B towards A, it is becoming 90 kip feet. Correct? But our aim to convert M over EI. So let's make it M over EI. 90 over EI kip feet. Correct? And that will be your loading in the conjugate beam W. And it is negative, so loading diagram will be downward. As we talked about, if the bending moment you get positive, loading diagram will be upward. Distances remain same, 6 feet and 6 feet. So to distinguish in between real and conjugate, let's make it A prime, B prime, C prime, so that you will not be confused in between real and conjugate beam. One thing I would highly suggest, once you make your conjugate beam, you need to forget real beam for time being, because otherwise you'll be confused because your support is going to be changed, your loading has going to be changed. So be very careful. You just need to focus on the conjugate beam. So once loading has been done, what is the next step? Step 2 will be change the support. So A was originally fixed in the real beam. It will be free A prime. B is just a point, no change B prime. C becomes fixed. Free becomes fixed. So this is your conjugate beam. Correct? So we have drawn our conjugate beam. We need to convert the triangular loading to equivalent concentrated load. So let's do that. Have 90 over EI times 6, which is becoming 270 over EI, and it is acting 4 feet from B to third. So our aim to find out slope and deflection at point C in the real beam, which will be your shear and moment in the conjugate beam, correct? So let's apply our static equilibrium equation. So summation of Fy is going to be 0. So what are the loads acting? 270 over EI, which is acting downward, negative. And at point C, your shear is downward, negative. So that gives your Vc prime is negative 270 over EI. Correct? So this is your conjugate beam. Conjugate beam shear. Real beam. Slope. So theta C real beam Vc prime conjugate and it is 270 over EI, negative, so it is going to be clockwise. We talked about that. Negative is clockwise for slope. So first part is known, theorem 1. Slope at any point in real beam is numerically equal to shear at corresponding point in the conjugate beam, which is point C. Now finding the moment, which will be equal to vertical deflection. Take the moment about C. If you see very carefully, what you are having, MC is counterclockwise, and this load is create moment counterclockwise, 6 plus 4, 10 feet. So MC prime counterclockwise 270 over EI times 4 plus 6, 10 feet. It's going to be 0. So MC prime will be negative 2700 over EI. So moment in conjugate beam again will be equal to vertical deflection in real beam, delta C. And we get negative value. So that means it is acting downward. And we know from the deflection diagram, we'll show one more time how it is acting. So we computed both slope and deflection and we got our direction. So let's recapitulate one more time. So if you see the deflection diagram, it is acting downward at point C. If you see the slope at point C with the tangent, it is acting clockwise. So that's what we got. By any chance, if you see that you are getting opposite part, that means you are doing something wrong in your calculation. So we got our magnitude of slope and deflection at any point in a beam by using conjugate beam method. Now I'm going to show you your practice quiz problem. So the last slide will give you the practice quiz problem. What you need to find out: displacement and slope at point C of the beam. It is one side pin, internal roller, and only one loading, which is the external moment, is acting at the free end of the beam. So you need to use conjugate beam method to find out slope and deflection at point C.